Hello everyone. First of all, my sincere apologies for having to cancel class today. Um, although university is open, there has been reports of a lot of snow, up to about a foot or more, and I felt it is better to be safe and warm, and than risk coming down to school. I will present most of the lecture that we are supposed to cover today as a video, and I will also be available for the office hours tomorrow at the regular scheduled time, just in case there are any issues pertaining to the material. So please feel free to email me or come down to my office in case there are any questions regarding any of the material we present today. The other announcement that I had for today's class is that I am expecting to provide a video also of the Hadoop installation instructions. I suspect that many of you are already familiar with installation of Apache Hadoop on a single node machine, on a single node on your machine, but it's also possible to install it in a pseudo-distributed mode. And for this I hope will provide the basic instructions for getting Hadoop installed on your system. And I think this would be an essential step for those of you who do intend to work on your projects with Apache Hadoop and have no prior experience. I will also try and post similar lab works for MongoDB, as well as for other labs that we might have. I must mention that none of this would be explicitly important in your quizzes, where most of the theoretical material will be covered. However, for your own benefit and for understanding the material that we cover in class better, it is almost imperative that you perform the lab works on your own. And I will post short videos of these labs throughout the course of the semester. The final announcement that I have is that next Monday, which would be, I believe the 9th of February, we are expecting to have a guest lecturer for our course. He's the CTO of a company called Protestify LLC, and he will talk to us about how big data technologies are being used to analyze protests all over the world. I'm hoping that we will have class as scheduled, but the last half hour would be where he would give us a demo of our system, as well as be available for general questions. And this would hopefully be a nice way for you to get acquainted with some of the ways by which the big data technologies are being used in the industry. Okay, now moving on to the material that we would cover today. We stopped last time after a short discussion about the 3 V's that concern big data. In particular, we talked about the volume of the data, variety, and velocity. And we also said that there was a 4th V pertaining to value or veracity that is sometimes also talked about in literature. And then we discussed briefly about how volume plays a very important role in analyzing big data. So the idea is that we store everything these days, be it environmental data, financial data, medical and surveillance data. And some examples of the kinds of data that we collect could include, for instance, taking a smartphone out of your pocket and to generate an event. Another example, the Department of Transportation is often interested in knowing exact details about, let's say, when commuter train doors open for boarding and so on. The airline industry is, of course, collecting a lot of data, and some of the data is pertaining to when the passengers are checking onto a flight at a particular time. And most of you have heard about recommendation systems, which either recommend songs from iTunes, books from say the Amazon.com, or so there's a lot of data that is available and can be used when building such recommendation systems. So the bottom line is all of the above actions generates a lot of data, and really, the organizations don't know how to manage this data and are typically overwhelmed by it. And so, part of the responsibility of learning big data involves trying to figure out mechanisms by which this data can both be managed very well, in terms of storage as well as development of different analytical techniques, which would give the organizations an upper hand in terms of being able to analyze and learn from this data. In the last class, we also talked a little bit about what is known as the blind zone, wherein a lot of data is available to an organization, but the percentage of that data that can really be processed is much lower. And as you can see in the graph here, it's obvious that the amount of data far exceeds the amount that can be processed. And so the question that typically arises is even trying to understand whether processing of this data will actually help an organization in any way. For the managers, this is a very important decision that they may have to take, and sometimes looking for useful information in this big data realm could often be like looking for a needle in a haystack. So there's a lot of volume as far as big data is concerned. The other the other important aspect of big data is pertaining to the variety of the data. So, for instance, data in an enterprise has become complex with the explosion of smart devices and sensors. There are sensors of different kinds that record a variety of different things. The smart devices like iPhones, iPads, and so on also collect a lot of data. The different types of data that are captured involve, of course, the traditional databases, but also a lot of raw data from semi-structured and unstructured relational databases such as weblog files, web pages, search indices, social media forums, emails, documents, sensor data from active and passive systems, and so on. So really the problem is that the data that is collected from these smart devices and sensors is not only structured and fits well into relational databases, but there's a lot of other things, semi-structured and unstructured data that adds and that has the potential of adding value to these relational databases. For instance, a very simple example would be to consider, let's say, the text that is easily available from, say, Twitter feeds. It is one thing to have the actual structure of the Twitter feeds in a relational table, such as in a JSON format, but then there's also information that is available as text in unstructured in the tweets themselves, which is of course unstructured, and not to mention the images and videos that are stored in relational databases, that are not stored in relational databases. So these are also examples of how big data can be used. So if one were to use, let's say, Twitter feeds to analyze a certain phenomena, and we were discussing rumor versus non-rumors in the feeds. Um, one could just look at the text from the Twitter itself, or one could also look at images, videos, retweets, and carve out special features which would help, let's say, a classification task like rumor versus non-rumor classification. So therefore, the problem that big data also faces is the fact that there's a variety of different kinds of data: text, images, videos, and several other kinds of semi-structured and unstructured data, all of which must be studied perhaps in association with their relational counterparts. So enterprises in general must be able to analyze all types of data, relational and non-relational. So for instance, text, sensor, audio, video, transactional, and more. So you can clearly see that the problem is not only just about processing the data, but also trying to understand whether some meaningful knowledge can be mined from this plethora of data that is now available to us. So big data is also about variety. The final thing that characterizes big data is, of course, velocity, meaning how fast is fast. The velocity at which data is generated needs to be handled. So it's not simply about the rate at which, say, a relational table grows. It's much more than that. And the idea is that to be able to analyze the data as soon as it is getting generated. So it's the speed at which the data is flowing. The goal is to identify trends and patterns in real time, perhaps only seconds or microseconds before someone else does. So, for instance, if giving the appropriate level of attention to the problem at an appropriate time uh, is very important. And by that I mean that in batch processing, for example, typically what is done is you get all of your data at one shot, and you look at the history and you learn some patterns. That's not really what is expected when people want to do online learning or stream mining, where the expectation is as soon as the data point comes in, you relearn your analytics modules and therefore redo your machine learning models. So there is, and this is, for instance, introduction of stream computing is a step ahead in traditional batch processing systems, and therefore systems such as Apache Storm, Store, and Spark and others have come into play. In general, for instance, an example would be, let's say you want to identify all people in New York who are in the path of a snowstorm, and suppose you want to do this using GPS information that is constantly getting updated, and maybe you are an emergency service that wants to send help to the people in the path of the storm, and the first part aspect of this is the fact that the GPS information is constantly getting updated, and therefore maybe your classifier just tries to do a simple classification of whether a particular person or a particular inmates of a particular house are in the path of a storm or not. So that's just the binary classification problem. But the problem becomes much harder because the features which will help you learn this binary classifier are essentially learned in an online or a streaming fashion, meaning that the features are available one at a time. So as and when you process one GPS coordinate after another, you're obtaining your features, and therefore not all of your data is available at one go. So there is a velocity aspect also associated with this big data. A few other things that are of consequence is to understand the difference between what constitutes a data in a warehouse versus, say, data in a parallel processing system such as Hadoop. Traditional data warehouses analyze structured data from various systems. They produce insights with known and relatively stable measurements. So the first key difference is that you usually store very structured data in data warehouses. The second aspect is that a lot of rigor goes into getting the data into the warehouse, which means there's usually somebody who is or somebody or a team of people who are responsible for cleaning the data, enriching it, if it's natural language, to match it against a dictionary, to check for some metadata, do some level of intense pre-processing of the data before it's loaded into a warehouse of some kind. So therefore, the warehouse itself, building of the warehouse itself becomes a very expensive process, because now you're talking about actually paying the people and involving and accounting for the involvement of these people who are actually going to clean the data. Note, however, that even though the data has been cleaned, we haven't necessarily done maybe any analytics on it. So the data warehouse has a lot of nice structured data which may or may not be useful for the task at hand. But usually, this data warehouse has a broad purpose, meaning that it is often used in reports, dashboards, etc. And therefore, the company that is hosting this data warehouse is okay with spending the amount of time and energy required to actually clean the data and to come up with the metadata and so on. In contrast, if you think of Hadoop-based systems, first of all, these systems are essentially very well suited for semi-structured and unstructured data, where a data discovery process is required. Now, the issue is that in Hadoop-based systems, it could be the case that no prior effort is made in cleaning the data. So you could have just maybe searched Twitter for some keywords, and you can get a bunch of tweets, and you can simply upload that data into a Hadoop-based system without doing anything further in terms of processing the data. The other alternative is that one could go into a lot of lengths to actually examine the tweets and identify features that may be useful for learning and so on. But usually, it is assumed that when data is stored in Hadoop, it is stored in a raw, unstructured form. And therefore, the initial effort that goes into building a warehouse is often not a key concern in Hadoop-based systems. But that said, if there were a need to develop a Hadoop-based system for structured data also, that may be possible without much problems. So big data repositories, such as those used in building Hadoop-like repositories, do not undergo the same rigor as those of the data warehouses. Prepping data for Hadoop use cases can be cost prohibitive, and data in Hadoop might seem of low value or unquantified as of today, But then there could be a lot of key to, but it could also hold the key to a lot of unasked questions. So while the data itself is very unclean and potentially contains a lot of noise, it is also useful because of the amount of potential value that it can have. An analogy that is often talked about in this context is gold mining. When a miner goes looking for gold, he may sift through large volumes of ores and minerals and so on and come up with a little bit of gold in a certain area, and that is often referred to as a nugget of gold, and therefore is of great importance to the miner. However, the same miner, when he gets, let's say, enthusiastic and he tries to look for more pieces of gold, the question becomes, should he look for gold in the same area where he's found, because he's sort of convinced that maybe this area has a lot of worthwhile information, or should he just go to some other place in the mine and start digging there, because the assumption is that maybe that part of the mine has, and of the ores and minerals and so on, have been explored. Now, there are pluses and minuses and pros and cons to both of these scenarios. The first one being the fact that the miner relies on his prior experience and prior knowledge and so on. But then the cons of that are that he may or may not find more gold, just because he's found a little nugget here doesn't necessarily mean that he will get the same kind of value from sifting the ore at the place that he is. And similar arguments can be made about him going to another location and they're digging there. Just because he's found a new place doesn't necessarily mean he will get a nugget there, and even if he does, there's no guarantee whether he will get more information from there. So there's always this trade-off between whether how much of where to look for this gold in the mine, in the ores, and where to hunt for them and how to find that out. And so this analogy carries very well over to scenarios in big data. The nuggets that we are looking for primarily in the data are nuggets of useful information, meaning something that your competitors in the business don't know about, which you've somehow learned from the data. And the other analogy of the ore or the minerals that you're looking for is the availability of vast amounts of data. And then the question becomes, how do you actually use all of that in a meaningful manner? A few other things that we might need to talk about. One is the notion of value per byte, and also the notion of cost per compute. Now, some of this, needless to say, sounds very vague, because how does an IT manager really know that whether there is any value in going the route that he or she is planning to go? And so the literature has come up with some metrics of measurement, and two of those are value per byte and cost per compute. So it says the IT departments would like to have a high value per byte of information that is processed, meaning that if you get nuggets for every byte that you've processed so far, you're probably doing very good. But really, big data has low value per byte, because you could be sifting a lot and lots of data, but the nugget that you get is maybe something not as meaningful, and maybe some knowledge that you are already aware of. So big data usually has low value per byte. But there are potentials for new insights, and if all of the data can be analyzed. The other aspect that is of importance is the notion of cost per compute. In traditional databases, the cost per compute is high, so data is clean and proven and known to have a higher value per byte, but usually this is low in the case of Hadoop-based systems. Um, the reason it is high, the cost per compute is high in a traditional data warehouse, is because in a traditional warehouse, in order to get your data processed and cleaned, one would require to put in a lot of effort, just as we talked about a while back, and therefore all of those basic costs do come uh, into consideration when you actually come up with a cost per compute. So just to recap, the goal is to mine for nuggets of information, and it is often hard to sift through all the data that is available in traditional processes. There's too much with little known value and expensive to look through. So we need analytics for data at rest as well as data in motion.